So this is my Unit 2 chemistry revision, so it's kind of like a part 2. This is for the second exam, and this is AS, so Unit 1. So we're going to start off with enthalpy change. So the definitions first. So standard enthalpy change, the heat energy change at a constant pressure under standard conditions, which is 100 squared kilopascal, 298 Kelvin and 25 degrees Celsius. Standard molar enthalpy change of formation, the enthalpy change when 1 mole of a compound is formed from its elements under standard conditions. Standard molar enthalpy change of combustion, the enthalpy change when 1 mole of a compound is completely burnt in excess oxygen under standard conditions. Mean bond energy, the energy required to break a covalent bond, shows strength of bond, and the value is bond energy per mole, which is E. Bond enthalpy, the enthalpy required to break 1 mole of a covalent XY bond into X and Y atoms, all in the gas phase. The values are always positive, which means it's endothermic. Average bond enthalpy, the average value of enthalpy required to break a given type of covalent bond in the molecule of a gaseous species. Hess's law, the process of measuring the amount of heat released or absorbed during a chemical reaction. By knowing the change in heat, it can be determined whether or not a reaction is exothermic or endothermic. Collision frequency, the number of collisions between particles per second. Collision energy, combined energy of the colliding particles. Activation energy, the minimum amount of energy required for a reaction to take place by breaking bonds. Catalyst, a substance that increases the rate of a chemical reaction without itself undergoing any permanent chemical change. It provides an alternative route which uses a lower activation energy. Some equations, you need delta H equals heat over moles, Q equals mc delta T, which is Q equals heat energy, M is mass of the substance in kilograms, C is specific heat, which is 4.18, and delta T change in temperature, and it must be in Kelvin. So enthalpy of formation, the arrows always have to be pointing up, and combustion always have to be pointing down. So measuring enthalpy changes, I've already said the equation. Specific heat capacity, which is C in the equation, the amount of energy needed to raise the temperature of 1 gram of substance by 1 Kelvin. Some experimental errors, you may get a question on this. It means we don't calculate heat loss to the surroundings. So that's why if they've calculated something and what we've actually got, if there's a difference, it's because we haven't calculated to heat loss, which happens in an actual experiment. So if that question comes up, you have to say that. Calculating enthalpy change of reaction. Step 1, calculate the heat lost or gain using Q equals mc delta T. Then convert joules to kilojoules if you need to by dividing by 1000. Then step 2, calculate moles of one of the reactions that caused enthalpy change. So moles equals mass divided by mR. Then step 3, calculate delta HR in kilojoules per mole using delta HR equals Q divided by N times the number of moles reacting in the balance equation, if there is a different number in the equation. Hess's cycle, the enthalpy change for a chemical reaction is independent of the route taken. So you could have the actual equation, and then below it you have another route which is independent to the actual route it takes. Route 2, the total enthalpy change is the same for route 1 as route 2. Note the enthalpy change for elements is 0. The element is being formed from the element, so there's no change in enthalpy. Enthalpy of formation, in the equation you must add standard states. So step 1, draw and balance the formula equation. Step 2, write and balance the elements of one side of the equations underneath it, which is like route 2. 3, draw arrows pointing up. And then 4, draw a clockwise arrow in the center. By doing this, when you go around the circle, when you go against the arrow, you have to put an equal sign, and then it could go out as delta HR plus delta H1 equals delta H2. Enthalpy of combustion. Combustion equations always make CO2 plus H2O. Substances which do not support combustion, like water, carbon dioxide, and most other oxides, have 0 enthalpy of combustion. It is always negative, which means it's exothermic, and to draw it, You must write and balance a combustion equation, then write underneath the equation the combustion equation and balance it, and then draw the arrows all facing down and draw a clockwise arrow again. Bond enthalpy, the energy change is equal to breaking, take away, making. B comes before M in the alphabet. Rate of reactions. Why not all collisions lead to a chemical reaction? Not all particles collide, leading to insufficient energy to activate a reaction, which may lead to an incomplete reaction. Only occurs if the colliding particles have equal to greater than activation energy and needed to be in correct orientation. Maxwell-Boltzmann Distribution. The graph does not reach zero as no molecules have zero energy, so it goes up and then comes back down. The highest point is the most probable energy, and then later on it says average energy, and right at the end it would say activation energy, which is the part where the molecules would be reacting. When there's a temperature change, the lower temperature means that the graph is moved to the left and the peak is higher. A higher temperature means that it is moved to the right and the peak is lower, so it goes like that more, then that more. Concentration, the most probable energy of the molecules stay at the same area, but the peak would be higher at the same energy value. When there's an increased area, when more total reactant molecules are at the same temperature, increase the number of reactant molecules which can undergo a successful reaction, so the activation energy is bigger. For a catalyst, it provides an alternate reaction route or pathway. It lowers the value of the activation energy. The area above the activation energy is greater. There are more molecules with sufficient energy to undergo a successful collision. A catalyst does not affect the shape or of the distribution as long as the temperature and total number of molecules are not changed. A heterogeneous catalyst is a catalyst that are in a different phase the reactants. So it could be a gas catalyst and they are liquids. A heterogeneous catalyst, the process. So I've learnt it as hard, H, heterogeneous, A, adsorption, which is a stick-on catalyst, R, reaction, and D, desorption. So step 1, adsorption. The reactant molecules are absorbed onto the active sites of the catalyst. The bonds inside the molecules start to break. Step 2, reaction. The molecules are held at a favourable angle so that the collisions can occur. Step 3, desorption. Product molecules are free to leave the catalyst. The catalyst is left unchanged, just like all catalysts. A homogeneous catalyst is a catalyst in the same state as the reactants molecules. You'll need to know the iodine clock method. So step 1, in separate conical flasks, make up the solutions, which is 10 centimeters cubed of sulfuric thiosulfate, 25 centimeters cubed of potassium iodide, and do not add hydrogen peroxide yet. Add 1 centimeter cube of starch solution to each flask and mix thoroughly, then rapidly add hydrogen peroxide to flask 1, starting the stopwatch immediately after, then swirl to mix the reaction thoroughly. Stop timing when the solution has turned blue-black and record the time. Contact process is an example of a heterogeneous reaction where a catalyst changes oxidation state during the reaction. So the sulfur dioxide is oxidized to sulfur trioxide by vanadium oxide, and the vanadium oxide has been reduced to vanadium 4, and it was 5. It's V2O5, now it's V2O4. It is oxidized back into vanadium 5 oxide by oxygen. So you just add excess oxygen and then it's left unchanged. Catalytic converters. It removes harmful gases from car exhausts, consists of honeycomb and ceramic with metals, platinum and rhodium. It removes up to 90% of harmful gases, and support medium is used to maximize surface area and cut costs. The Haber process. This is where N2, which is gas, plus 3H2 converts into 2NH3, which is ammonium, and it's a equilibrium, so it can go back and forth. The catalyst, which you need to know, is iron. Sulfur poisoning in process. Hydrogen obtained from natural gases, which is contaminated by S. If not removed, the iron would absorb into it on its surface, poisoning the catalyst. To reduce catalytic poisoning, you must purify the reactants. Impurities can be absorbed by a catalyst, removing potential sites. It becomes expensive because it must be replaced and the process must be shut down. Iodide ions and persulfate ions. The reaction is very slow without a catalyst because the reaction needs a collision between two negative ions. The repulsion between the ions is stopping this. The catalyst used is the iron again. Persulfate ions oxidize the ion 2 into ion 3. By oxidizing the iodide ions back to iodine, the ion 3 is reduced back to ion 2, so it's unchanged. Both stages involve collisions between positive and negative ions and will have a lower activation energy than with two negative ions. Organic compounds. Functional groups. So ones you may need to know that you may not know already. Aldehydes means al at the end of the word, and it must be on carbon number 1 or the other side. Depends which side you're on. A ketone, it says "one" at the end of the word, and it's always in the center. That's the difference between an aldehyde and a ketone. A carboxylic acid has got oic acid at the end. Halogenoalkanes, it says chloro, bromo, and iodo. For example, 1-bromobutane. Types of formulas. Displayed formula. All atoms and covalent bonds are shown. Structural formula shows the arrangement without the bonds. Skeletal formula doesn't show carbon or hydrogen atoms but does show other atoms. Isomerism, same molecular formula but different structural formula. So a chain isomerism, more than one way of arranging longest chain of carbon atoms. They can have a different length chain. So one example would be pentane, 2-methylbutane, 2,2-methylpropane. Positional isomerism, some functional groups but attached at different points. So it could be at the end or it could be in the middle. Functional groups, different functional groups, such as going from an aldehyde to a ketone, so moving the COO bond and the H to the middle or to the end. And we have some more definitions. So electrophile, an electron deficient species that can accept a lone pair of electrons. A nucleophile, a species with a lone pair of electrons that can be donated to an electron deficient species, such as an electrophile. A radical, a species with an unpaired electron. Homolytic bond fission, when a bond is broken and each of the bonded atoms receives one of the bonded electrons. Heterolytic bond fission, when a bond is broken and one of the atoms receive both of the bonded electrons. Halogenoalkanes, polarity decreases in electronegativity down the halogen group, so the polarity decreases. Nucleophilic substitution, so the weaker the bond, the more easily it breaks, which means a faster reaction. So Ci has a faster reaction than Br and Cl and F. The conditions is that it must be aqueous and warm. What happens is that a halogen atom is replaced by an OH group. Also, I must note, in NH3 there's 2 steps, so you have to look out for that because there's 2 NH3s. So you add one and then you add the other one afterward. Then there's elimination. You need to look over that. It's where instead of adding something on, you react the OH in it and then you take off a H, which makes H2O, and then the Cl or halogen is taken off and reacts with the K. So it would be KCl plus H2O. Uses of halogen alkanes as solvents. Halogenoalkanes contain a polar section and a non-polar section. This means that they can mix with many organic substances, and the non-flammability means that they can be used in dry cleaning clothes. Chloro compounds were preferred as they were cheaper. Anesthetics. Trichloromethane was one of the earliest substances to be used, but is no longer used where halothane is still used. Refrigerants. Permanent dipole attractions means that their boiling point is close to room temperature, so they are liquids that can be easily evaporated. CFCs were used, which is non-flammable and non-toxic, which is important for this use. Regulations. The use of halogenoalkanes is limited by regulations because polychloroethylene alkanes are toxic and CFCs can damage the ozone layer. Free radical substitution. Stage 1 is initiation, where 2 chlorine atoms break up to 2 chlorine free radicals using UV light, and this is done by homolytic fission, which means breaking of a covalent bond to create free radicals. Stage 2 is propagation, which is a chain reaction, and you need to know the mechanism but also the overall equation, which is CH4 plus 4Cl2, and it makes CCl4 plus 4HCl using UV light again. And then stage 3 is termination, which stops the chain reaction and 2 free radicals are forming a new bond. CFCs. Up in the atmosphere, CCl bonds break because it's no longer the standard conditions down here where it makes it stable. It is no longer one atmosphere but there is insufficient energy to break the CF bonds, which means only the CCl bonds break. The Cl bonds make a radical which makes a chain reaction because it's trying to react, and it turns the O3, which is the ozone, into oxygen, which is creating a hole in the ozone. The overall equation is 2O3 and makes 3O2. This is a reversible reaction, yet the Cl radicals up in the atmosphere has forced the forward reaction to move at a faster speed, which means the ozone is quickly going to oxygen a lot faster than it's going back. Hydrocarbons. The boiling point of alkanes. The longer the carbon chain, the higher the boiling point, due to the stronger van der Waals forces between the molecules. The more branched the chain, the lower the boiling point, due to the weaker van der Waals forces. Molecules can't pack close together. Fractional distillation. Crude oil is formed by a slow decay of marine animals and plants over millions of years under heat and pressure and no air. Crude oil has no use in its raw form, so it's separated into fractions by the differences in physical properties. The separation process. Crude oil is vaporized. Vapor is passed into fractional columns, which is hot at the bottom and cold at the top. As the vapor rises, it cools. Molecules will condense at different heights as they have different boiling points. The larger the molecules with higher boiling points, the lower down the column it condenses. This produces fractions, a mixture of hydrocarbons with similar boiling points. As the chain gets longer, it becomes more viscous, harder to ignite, less volatile, and a higher boiling point. Cracking. Shorter chains in more demand than the larger fractions. Cracking is thermal decomposition of alkanes, and C-C bonds are broken in cracking. Thermal cracking is used in 900 degrees Celsius, 70 atmosphere, no catalyst, and it produces alkenes. In catalytic cracking, it's in a lower temperature, which is 450 degrees Celsius. It's in 1 to 2 atmospheres, which is less dangerous, and it has a catalyst of zeolites, which means it'll be faster, but this creates motor fuels. Reforming. Process where straight chain hydrocarbons are converted into branched chain alkanes. This burns more efficiently and are used in petrol for cars. Combustion. It's highly exothermic. If it produces a complete combustion, it creates CO2 and H2O. If it's incomplete, it creates CO and or C. Formation of sulfur dioxide. Sulfur is found in fractions, which means when burned, it can cause acid rain. It can be removed by flue gas desulfurization. Gases pass through a scrubber containing calcium oxide or calcium carbonate with sulfur dioxide. Reaction forms gypsum, which creates plasterboard. Is isomerism. So bond number 1 is a sigma, which is like a circle with a little line. A covalent bond. The electrons are between 2 carbon atoms, so it's just like a... And then the second bond is the pi bond. Electrons above and below the plane of the central atoms. So you have the CC bond, and then it's like all around the top and the bottom. Stereoisomerism. Molecules with the same molecular and structural formula, but a different arrangement of the atoms in space. You would have to break CC double bond to rotate, because it doesn't rotate around the CC bond. If both C's of the CC bond have 2 different groups attached, it has an EZ isomerism. The E isomer means the higher priority is opposite, so one's at the top and one's at the bottom. And the Z isomer is on the same side, so they're either at the bottom or the top. And the priority means it's got a higher atomic number. It also means that you need all four of the things on the top and the bottom to be different. These can be the same, but these need to be different. Electrophilic addition. Basically, C-double-C bonds break and form a new bond with a halogen. Direct hydration. The reagent is steam. The conditions are high pressure, and the catalyst you need is a phosphoric acid. This is used for ethanol manufacturing. Hydrogenation. The reagent is hydrogen, and you need a nickel catalyst, and this is used for margarine manufacture. Testing for alkenes. Bromine water decolorizes in alkenes. The brown bromine turns into colorless, and in an alkane there's no decolorization because it's saturated and alkanes cannot react. Addition polymers. A polymer is a large molecule made from lots of small molecules called monomers joined together. Polymerization. The process in which monomers join together. Two types of polymers are addition polymers, where no other products are formed, and condensation, where smaller molecules such as water is lost. You need to know what the uses of some polymers are. So polyethylene is used for packaging such as bags and bottles. Polypropylene is for crates and ropes. Polyphenolphthalein is for packaging. Polychloroethene is for window frames. Polytetrafluoroethene or PTFE is for non-stick frying pans. Polymethyl 2-thiopropanoate is superglue, and polymethyl 2-methylpropanoate or perspex is used for windows. Mass spectrometry. Points to look for in the IR spectrometer. If there's a broad peak around 3,300, there's an OH bond, which means it's an alcohol. If there's a thin zigzaggy line at 3000, it means there's a CH bond. And if there's a long thin peak at around 1600, 1700, it shows a COO bond. And if there's a short thin peak around 1600, like end of 1600ish, there's a CCC bond. In the mass spec, if there's a peak at 15, that means there's a CH3. There's one at 17, there's an OH. If there's one at 29, there's a C2H5. If there's one at 30, there's a COH2 bond. And if there's one at 43, there's a C3H7 bond. The highest peak means base, which means it's the most abundant, and the molar mass, MR, is the highest MZ, not the tallest. HNMR, the environment. Different environments have different amounts of H's, hydrogen, and also different bonds next to it. For these types of essays, you need to know the chemical tests, so I'll go through them now. Bromine water turns from orange to colourless with a CCC bond. If you add acidified potassium dichromate, primary and secondary alcohols can be oxidized into carboxylic acid, and it's also used to identify aldehydes. If you add sodium carbonate, if it fizzes, there's carbolic acid, and if you add potassium permanganoate, then if it turns purple to colourless, there's also a CCC bond present. Green chemistry, the final topic. To make little impact on the environment as possible, we must try to prevent waste, increase atom economy, use safer methods, chemicals and solvents, increase energy efficiency, use renewable raw materials, plant-based compounds, and use catalysts and design for biodegradation. And that's everything for Unit 2. Good luck!